we've talked about the photoelectric effect, in which Einstein showed that light, which people used to think was just waves, also had some particle-like properties. And we called the particles photons, and that they delivered a certain amount of energy every time they hit. The energy was quantized, which basically means it just comes in lumps. And you can imagine those lumps are just individual particles of light landing on the surface of a metal, so that all of the energy of that particle gets delivered at once. There was another thing going on at the time. Again, people were trying to figure out the structure of atoms. And if you recall, there was this picture of the electron going around the nucleus in some sort of orbit, much like planets go around the sun in an orbit that's just an elliptical orbit. The problem with electrons is we know that accelerated charges emit electromagnetic radiation, which causes them to lose energy. And as they lose energy, they will spiral into the nucleus, collapsing all matter on itself and destroying life as we know. Okay. So that can't possibly work. The solution for how electrons can be in orbit around an atom and still not collapse into the nucleus was actually provided by a man named Niels Bohr. And he got this idea from something that de Broglie had come up with. So de Broglie sees all this interesting stuff happening in the modern physics of the early 20th century. He sees the photoelectric effect. He notices that waves, which we use for electromagnetic radiation, which we used to think were just waves, also have some particle properties. And de Broglie basically said, hey, what if electrons and other particles, things that we used to think were just teeny tiny little balls, what happens if they also have wave-like properties? So that was his big intuitional leap here. And what he said was this: if you take an electron or a proton or any other piece of matter, that matter also has wave-like properties, which means we can define some sort of wavelength to that. Now, how do you determine what that wavelength is? Well, de Broglie wrote down this simple formula. This is your de Broglie wavelength. And the de Broglie wavelength depends on the how fast the particular particle is moving. And it depends in this way. It's h over p, where p is the momentum. So that's h over mv. So that's your velocity, that's your mass, that's your momentum. The h is Planck's constant. So de Broglie has this idea that particles, things that we used to think were just particles, also have some wave-like properties. Now, what exactly does that mean? Suppose you take an electron. Give myself more room. Suppose we take an electron and we start firing it at some target. Well, we know that if I were firing waves at a target, specifically, let's say we're firing it at a hole that has two slits in it. Well, if it were waves coming through, we would get this interference pattern where you'd have alternating peaks of constructive and destructive interference. Places where, if it were a water wave, the water wave in some places would combine constructively, so you get a big peak in the water, big amplitude, and some places where it would combine destructively, so that those two the waves coming from hole number 1 and hole number 2 would cancel each other out. What happens if you do this with electrons? Suppose we do this with electrons. Well, we know electrons come all at once. It's not like a wave where I can get some amplitude in between other amplitudes. Right? Nothing, if I have a water wave, nothing says that the water wave has to have an amplitude of 1 meter. It could be 0.9 meters or 0.8 meters. But when we talk about electrons, you always only get 1 electron. You never get 0.9 electrons. However, even with that as the case, what you find is, when you counting where the electrons go, you get a lot of electrons in certain spots. And no electrons in other spots. So it appears we've got these regions where we get no electrons showing up. And those regions, you can describe that as being regions of constructive, or destructive rather, destructive interference. Right out of room there. Those are regions of destructive interference, and the regions where you get a lot of electrons, those are constructive interference regions. Constructive interference. So our electrons have interference patterns just like water waves and just like light waves, which can be a little bit confusing. But we know that the math works out this way. So we know that the electrons must have some wave-like properties. And the wave-like properties are just governed by that de Broglie wavelength equation. Lambda equals h over p, where p again is just the momentum of the electron. In fact, this is not just true for electrons. People have done experiments with other objects, buckyballs. In principle, it's also true for baseballs and tennis balls and any sort of object. For you, as you're passing through, you have your own wavelength associated with you. Now you might ask, well, why don't we see these interference effects in everyday life? And the reason is pretty simple. If you look at that wavelength equation, if we look at this wavelength equation, let's say you want to compute the wavelength for a person running down the street, or walking down the street. Suppose, well, let's just plug numbers in. You've got a Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds. Let's say you have a person who has a mass of, let's say, 60 kilograms. And we'll say 66 kilograms to make my math a little bit easier. And they're moving at 1 meter per second. Well, let's see what happens. 66 is going to cancel out with the 6.6. We'll be left with a 10 down here. So that's 10 to the minus 34 divided by 10. So that's going to be about order of magnitude 10 to the minus 35 meters for my wavelength. Now that is a ridiculously small wavelength. To put that into context, an atom is about 10 to the minus 10 meters. Okay, so let's say we shrink you down to the size of an atom. Okay, so you're teeny tiny. You look around, there's hydrogen atoms all around you. They're bumping into you. They're about the same size as you are. You're still nowhere close to being 10 to the minus 35 meters. Let's shrink you down again. So now let's shrink you down to the size of an atom twice. So you shrink down to the size of an atom. And then you're like, wow, I'm really tiny. There's all these hydrogen atoms around. Now let's take your tiny self and shrink you down again by the same magnitude. So we'll shrink you down by another factor of 10 to the minus 10. So that gets you to 10 to the minus 20. Now you're smaller than the nucleus. You're about 100,000 times smaller than the nucleus of an atom. In fact, that's still nowhere close. We've got to shrink you down again by a factor of 10 to the 10. It's about 10, we'll shrink you down by a factor of 10 billion. So that gets you to 10 to the minus 30 meters. You're still 100,000 times bigger than the wavelength of a person who's just walking down the street. This is why we're never going to see these effects for big macroscopic objects. Because you have to shrink yourself down 10 billion times 10 billion times 10 billion times 100,000 times in order to be able to see these effects, in order to be on the size scale of that wavelength. Now, if I do the same experiment, except instead of a person, I plug in the, let's say, an electron. So an electron's mass is 9.11 times 10 to the minus 31 kilograms. So much, much smaller. I've got a much, much smaller number in my denominator. That means overall my number is going to be a lot larger. So I'm just going to do an order of magnitude estimate here. Let's say this, I'm going to round both of these numbers up. This will get me to 10 to the minus 33. This will get me to 10 to the minus 30. I take this minus this, so that'll get me 10 to the minus 3 meters, which is a wavelength of about 1 millimeter. And a wavelength of about 1 millimeter, that's something that you can notice. Because unlike 10 to the minus 35 meters, a millimeter is something we have everyday experience with. We can see interference effect for waves that have a wavelength of 1 millimeter. Small, but something we can certainly measure. And the only reason for the difference in the numbers is that the electron mass is so very, very tiny. So that when we plug it in the denominator here of de Broglie's wavelength formula, we get a much larger wavelength. Something that's appreciable enough that we can actually measure it. If matter has a wavelength associated with it, there's going to be obviously some changes to how we understand and how we interact with that matter. And Heisenberg was able to figure out a very fundamental, important part of what it means to interact with matter that has both wave-like properties and particle-like properties. And one of the most fundamental things in all of physics is this idea of the uncertainty principle. Now, the uncertainty principle is commonly stated that you can never measure an object's position and velocity at the same time. So an electron's driving down the street, a cop pulls him over, the cop says, do you have any idea how fast you were going? And then the electron says, no, but I can tell you where I am. The uncertainty principle says you can never know where you are and how fast you are going. But that's actually different than the way understanding this is a little bit more tricky than you might suspect, because commonly it's said that you can never measure how fast you're going and where you are simultaneously. But it's actually a little bit weirder than that. It turns out that if you measure an electron's velocity very precisely, it doesn't have a well-defined position. Conversely, if I measure where an electron is very precisely, its velocity doesn't exist. There's a large uncertainty to it. So we want to talk about what we mean by that. Let's suppose for the moment that particles really do have wave-like properties, because all of the evidence suggests that that's the case. So let's say here's your particle wave. It's got some wavelength to it. A pretty well-defined wavelength too. We can look at that, we can measure the wavelength. However, in order to have that wavelength, I can't really say where the particle is. There's some big uncertainty, delta x, that determines where the particle is. I know it's somewhere in that wave, But if I know its wavelength very well, then I don't have a very good idea of where it is, because by definition, to have a wavelength, the particle has to be spread out so that you can measure that wavelength. So if we know the wavelength well, then we can use de Broglie's formula to figure out the momentum very easily, but that means I don't know where the particle is. Conversely, there's nothing that says the wave has to be sinusoidally shaped. I could have a wave that's just one big high peak. So let's say my wave looks like this. And we say, ah, that's very, very good. I know where my particle is. It's right there. It's only one big peak. There's a very small uncertainty there. Then we ask, what's the wavelength? So the wavelength, we don't know. It's a bunch of question marks. Which means I have a large uncertainty in my wavelength, which means I've got a large uncertainty in my momentum. If I don't have a wavelength, I can't have a momentum by the de Broglie formula. So there's this trade-off. The more I know about where I am, the less I can have a well-defined wavelength, because that means the wave has to be very localized in one spot. It can't be spread out over some region. The better I know my wavelength, the less I know what x is. If it's spread out, I can measure the wavelength, but can't know what the position of it is. Since wavelength determines the momentum, we can't necessarily, there's no way we can know both where the particle is and what its momentum is. Not just that we can't know it. It doesn't have a very well-defined momentum. It doesn't have a well-defined velocity if I know exactly where it is. So this leads naturally to this idea that there has to be some uncertainty in either the position so there's going to be some error range on that position. We'll call it x plus or minus delta x. There's got to be some uncertainty in the momentum. We'll call that p plus or minus delta p. And if delta x gets smaller, delta p has to get bigger. If delta x gets smaller, the uncertainty in my position gets smaller. That's this case. But then I don't know the wavelength, therefore I don't know what the momentum is. My uncertainty in the momentum has to get larger. And Heisenberg was able to combine these expressions. This is actually a well-known result for not just particles, not just matter waves, but all types of waves, is that you can never have a well-defined wave position and wavelength at the same time. So what Heisenberg did was he took what we knew from waves, converted it from wavelength to momentum, just using de Broglie's formula. Momentum, Planck's constant over lambda, and then when you do that, you get something that looks like this. The uncertainty in the position times the uncertainty in the momentum has to be greater than Planck's constant divided by 4 pi. Again, this is just a result from what we know about waves. Now, let's be clear that this is a fairly small uncertainty, right? Planck's constant is very, very tiny. It's 10 to the minus 34. But what it does mean is that fundamentally, if I make delta x smaller, delta p has to get larger. There's no way. There's a minimum amount that this uncertainty in position and uncertainty in momentum, if we multiply them together, it's got to be bigger than some number. So if I make one of those uncertainties smaller, the other one has to get bigger. Now you might ask, well, what exactly is the thing that's waving when we talk about matter waves? Well, this gets a little bit abstract, but what we're talking about is a wave in probability. So where's the probability for a particle to show up in different spots? So for example, when those waves combine and you get the interference pattern, you have a high probability of being at of the particle landing in a spot where there's constructive interference, so you get the peak in the wave. And there's a low probability of landing in a spot where you have destructive interference, where the two waves cancel each other out. Now, once we have this probability interpretation of how the waves work, we can start doing calculations and figuring out how the matter should behave in different circumstances. And one of the classical examples of this is something called particle in a box. So suppose we were to put some bit of matter, an electron, let's say, into a box. Well, we don't want to treat it just thinking it's a little tiny ball because we know that's not entirely correct. So instead what we're going to do is we're going to treat it in all its full particle wave glory. And we're going to imagine what's going to happen when I put that electron in this box. Well, what wavelengths can it take? Well, we know the wavelength is h Planck's constant divided by the momentum. And putting a particle in a box means that we can only really have certain wavelengths. There are only certain wavelengths that are going to fit inside the box. The largest wavelength is going to be something that looks like this. It's a half of a wavelength, technically. Because I only have one hump here, we need both sides of that sine wave in order to put it in the box, put the whole wavelength in the box. So if my box has a length L, the absolute largest wavelength we could get is 2L, since we've got a half a wavelength in the box. We could also fit a full wavelength in the box. In fact, I could fit 1.5 wavelengths in the box. Now you might notice what we're doing is very similar to what we've done before with standing waves. And in fact, that's exactly what these are. For a box of length L, it turns out we can only get certain wavelengths. Those wavelengths, let's just list them off. 2L. In fact, I'm going to write these in kind of a screwy way. This has a wavelength 2L over 1. Its wavelength is 2L. Our next wave, I'm going to number these. We'll say this is n is 1, n is 2, n is 3. We could keep going further and further up. But L can be 2L over 1 for the n equals 1 wave. It can be 2L over 2 for the second wave. It can be 2L over 3 for my third wave. 2/3 of L, because again, the full wavelength is 2/3 of the box. And in general, hopefully you see the pattern building here. It can be 2L over n, where n has to be some integer. So we have this general formula for a wavelength. The wavelength is 2L over n, where n is any positive integer. That's nothing new. Those are just the allowed wavelengths for standing waves in on a string of length L. But this has pretty deep implications for the physics if I can only allow these certain wavelengths. So I'm going to give myself a little more room here. I just want to rewrite that formula. Lambda is 2L over n. Because what this means is if I can only have certain wavelengths, then I can only have certain momentums. If I can only have certain momentums, then the particle can only have certain energies. So let's see what energies our particle can have. At the moment, I'm imagining it's just a particle, maybe bouncing back and forth in the box. Particle wave, I should say, bouncing back and forth in the box. So there's no potential energy here. Which means the only type of energy I can have is kinetic. There's no interactions, there's no gravity, nothing. We're just going to keep it very simple. The only energy we can have is kinetic energy, which is 1/2 the mass times the velocity squared. Well, how does the wavelength show up in that kinetic energy formula? Well, I'm going to write my kinetic energy formula in a slightly different way. I'm going to say it's 1/2 mv whole thing squared, but that gives me an extra m, so I've got to divide by the m. Okay, so it's 1/2 mv quantity squared divided by the mass. Nothing too tricky there, that's just algebra. But mv is the same thing as the momentum. So it's 1/2 the momentum squared divided by the mass. And we know that our momentum, if I rearrange this equation, our momentum just depends on the wavelength. H over the wavelength. Which means, when I plug in, I'm going to get 1/2 h squared over the wavelength squared over the mass. Because the momentum is h over the wavelength. Okay? So let's just give ourselves a bit more room here. We're just doing algebra here. I'm going to keep deriving that algebra. Here, rewrite that line up top. So that's 1/2 h bar squared over lambda squared m. Now we're going to plug in. Now we're just going to plug in our wavelength. So our wavelength, if we plug that in, it's 2L over n. So we should get, when we plug in for the wavelength, that the energy, the nth energy, is going to be h squared divided by the lambda squared. The lambda has a 2 in it, so we're going to square that 2. We'll get 8 on the bottom when we multiply by this other 2. We're going to get, there's still an m in the bottom. There's an L squared because of the lambda, and times an n squared, which was also in the lambda. So the energy level, the nth energy level, for this nth standing wave that can be in the box, where again n is some positive integer, is given by Planck's constant squared divided by 8 times the mass of whatever particle it happens to be, divided by the length of the box squared, times n squared. Now this is pretty deep. If you put a particle in a box, what that means is you can't have no energy. I know that's a double negative. You can't have no energy. You must have some energy. A particle cannot have 0 energy. Because the lowest number I can put in here is n is 1. If n is 1, you still have some energy here. A small amount of energy, because h is a very small number, and we're squaring it up here. So this has to be a small amount of energy. You always have to have some energy. Now that number is going to get smaller and smaller as you make L bigger. But you always have to have some finite amount of energy. Not only that, you can't have arbitrary amounts of energy. The energy values that we can take have to be quantized. So we can only get certain amounts of energy. N can be 1, it can be 2, it can be 3. It can't be 1.5. It can't be 1.6. We have only certain energies that are allowed. So if I were to make a plot of that, here's your allowed energies. Let's say that's energy 1, that's energy 2, that's energy 3. Particle can have this energy, but no energy in the middle. It can have energy 2, but nothing above energy 2 until you get to energy 3. Now, how does the particle exchange energy now? Well, it turns out a particle can't have an energy between E3 and E2, but it can jump from E3 down to E2. Or it could jump from E3 potentially down to E1, or from E2 down to E1. Or it could jump up from E1 to E2. Do that one over here. It can make these quantized jumps. quantized jumps between the energy levels. How does it do that? How does it do that if energy has to be conserved? Well, energy does have to be conserved, so that energy has to go somewhere. And it turns out that that energy goes into making photons. So whenever a particle jumps from one energy level to another energy level, whenever a particle jumps from one energy to another energy level, you have some photon that gets emitted. And here's how we describe it. Let's say this is an electron. Since this is going to be most common for electrons because this is what's going to happen inside atoms. So we're going to say electrons can jump up or down in energy by absorption. Absorption, I think this is right. I could be spelling that wrong. Absorption or emission of a photon. How much energy does that photon have? Well, the energy is of the photon, it's going to get an energy Planck constant times the frequency, just as Einstein had described the energy of a photon before. But that's going to be equal to whatever the change in the energy was. E final minus E initial. So the energy of a photon that gets absorbed or emitted is just going to be equal to the energy that gets gained or lost when the electron makes a transition between energy levels. What we have in front of us here is a helium lamp, and what this is basically a tube of helium which is getting excited by some voltage being applied throughout the tube, and that's causing the electrons inside the helium tube to jump up and down between energy levels, and when they do that, they emit different colors of light. Now, this is different than just heating an object up and waiting for it to glow. And we can tell it's different because if we look through a diffraction grating, which I have here, the diffraction grating is going to split up this sort of peach color into all of its constituent colors. So let me just hold this up to the camera. And you can see off to the side there that we have very clear lines of color. We don't just get a big bright rainbow of color as you would get if you were just looking at a light bulb, let's say. We get very distinct lines of color. And the reason we see these distinct lines of color is because there are only certain energy levels. Again, the energy levels are quantized so that when the energy levels are quantized, there are only certain jumps that you can make. Or to put that another way, there's only certain photon energy levels that can be reached with these particular energy levels. In this case, the energy levels associated with helium. So we're only going to get very specific colors out of our helium lamp. So what we can do by looking at these colors is we can figure out the spacing between the energy levels. So you look there, we've got some energy difference that's going to give us red light, something that gives us yellow, a couple of blues, some purples. By knowing what the energy of each of those photons is, we can figure out the energy spacing in the atom, and we can use that to figure out something about the atomic structure. we have this picture of particles that says that not only do they act like teeny tiny little balls, but they also have wave-like properties. So we can apply this to actual atoms. We know how these matter waves work if we put them in a box. We get these quantized energy levels. We see the same sort of quantized energy levels if we look at the atomic spectra of atoms when we excite them. The electrons jump back and forth between the energy levels, which is why we only get discrete bands of color in the atomic spectra. Well, can we actually use what we've learned so far to make a model of the atom that actually predicts the colors that we see if we do an experiment? Well, it turns out we are not the first people to have that idea. Niels Bohr was probably the first, and he came up with this idea of modeling the atom using all of the bits of physics that we've discussed so far. And we know that at the time they had this picture of the atom where the atom goes around the nucleus, kind of like planets go around the sun in the solar system. But we need some way of getting around the fact that the electron would spiral into the nucleus because it would start to emit radiation. And Bohr's idea built off of de Broglie's wavelengths, de Broglie's matter wave, because essentially what Bohr said is that, well, let's, instead of putting our particle in a box and matching the wavelengths to the end of the box, let's put our particle in an orbit. Let's put our electron in an orbit around the atom and match the wavelength up as the electron goes around the atom, so that the wavelength has to match up. You have to have the same height of the wave when you start as when you finish. Since you're going around in a loop, you end up where you started. So I'm not going to derive this full formula for you. I'm just going to give you the math behind it and let you work out the algebra. But Bohr took a few bits of information. One, he said, all right, we know the formula for the electric force. K cubed charge 1 charge 2 over r squared, where K is the electric constant. So we know the force between our electron and our proton, or nucleus, whatever it happens to be. We know the centripetal force is just mv squared over r, and presumably if our electron is in a circular orbit, we've got some centripetal force. We have de Broglie's formula, which relates the momentum to the wavelength and also has Planck's constant in there. So we know the momentum of the electron is related to its wavelength. We know the total energy of the electron is just going to be the kinetic 1/2 mv squared plus the electric potential energy, which is K charge 1 charge 2 divided by the radius between the charges, the distance between the charges. And Bohr tacked on one more expression. He said that the circumference of that orbit, 2 pi r, has to equal an integer multiple of wavelengths. And you need that in order for the wavelengths to match up. So with these 5 formulas, Bohr was able to derive the energies that were going to be allowed as a function of that quantum number n. Remember, n is the number of full wavelengths that we have going around our loop. And if we combine those formulas together, you get a very simple formula for the energy. Here are the allowed energies that you can have. It's going to equal minus, so the bonded energies have to be negative because there's this attractive interaction. It takes energy to, I actually have to put energy in just to remove the electron and separate them far away. So we're going to start with a negative energy. It's going to be K charge 1 charge 2 whole thing squared divided by 2 h bar. I'll tell you what that is in a sec. Mass of the electron, whole thing times n squared. Now if you multiply this out, there's a particular unit that we like working with. It's called an electron volt. An electron volt is the amount of energy you would get if you take one electron and have it accelerate across a 1 volt potential. But this turns out to be, oops. All right, this should be a 1 over n squared, I believe. This turns out to be minus 13.6 electron volts divided by n squared. This is the nth energy level of our atom. He also found out a few other things, a few other predictions. He found out the radius of the atom, which was given by AB. I'll say what that is in a second. This AB is called the Bohr radius. What this formula basically says is that as you go up in energy level number, as you go up in n, the atom gets wider and wider. That Bohr radius, let's see, I want to put it up here. That Bohr radius is equal to h bar squared divided by mass K, charge 1, charge 2. And in shorthand, it's equal to 0.0529 nanometers. Now, I mentioned there's this H that has a bar on it. That's kind of by convenience. This H bar is just Planck's constant divided by 2 pi. The only reason we do that is it saves us the hassle of having to write that 2 pi over and over again. So I'm going to redraw my atom here. I'm going to draw a few different orbits. Because remember, these orbits are now quantized. The radius is quantized, so that we can only have orbits of certain radii, according to this model. And according to this model, we have an n equals 1 radii, an n equals 2 radii, and n equals 3 radii. And electrons can jump back and forth between those energy levels. When they do so, when they jump down an energy level, they have to emit a photon. When they go up, they had to absorb a photon in order to have enough energy to jump up that energy level. And you're going to get different colors based on how big of an energy level you've dropped. So if I drop from 2 to 1, I get a certain energy. If I drop from 3 to 1, I get a bigger energy photon that comes out. We can keep going. We can do the n equals 4 level. That will get a different wavelength and frequency of the photon. All of these drop-downs should emit some photon of light. Now, if the Bohr atom actually works, it should be true that the colors that we get out match the colors we just saw when we were looking at the atomic spectrum. It should match the colors that you'll see when you hold a prism up, the little lines of colors that you see when you hold a prism up to a hydrogen lamp. And it turns out that for hydrogen atoms, the Bohr models works just great. We get almost exactly the same colors that you see to within experimental uncertainty. It matches this nice formula where all we're doing is jumping back and forth between the different energy levels. So if you want to know let me give myself more room. If you want to know what happens when you jump down from the third energy level to the second energy level, we just look at our energy formula. We look at the change in the energy. If we go from the third energy level to the second energy level, all we do is we plug into that formula. We'll say it's minus 13.6 electron volts over 3 squared. minus minus becomes a plus, 13.6 eV over 2 squared. This gives you your change in energy. If I want to know what frequency or what wavelength the photon comes out, all you got to do is set that equal to Planck's constant times the frequency. That's the energy of the photon. And if I want to know the wavelength, all I have to do is solve for the wavelength using the fact that for any wave, the wavelength times the frequency gives you the wave speed. So this gives us a very powerful prediction tool that will, at least for hydrogen atoms, predict what colors are going to come out when we start to excite the electron inside the atom. So in summary, we have this model of the Bohr atom that says we get these different energy levels. And whenever an electron makes a transition between those energy levels, it is always emitting or absorbing a photon. So it could be that the electron jumps down an energy level, in which case it emits a photon with some energy, E equals hf. We could also do the reverse. If we have a photon with the right energy coming in, E equals hf, the electron could jump up from the first to the second energy level. And by conservation of energy, it must be true that the change in the energy of the atom is equal to whatever the energy of the photon that gets emitted or absorbed is. And that's just given by Planck's constant times the frequency. As successful as the Bohr atom was at describing the hydrogen atom, and also hydrogen-like atoms, by which I mean atoms that only have one electron, it failed pretty miserably when it came to any sort of other atoms, atoms that had 2 or more electrons. So helium, if it wasn't ionized, Bohr model couldn't describe. Lithium, basically everything else in the periodic table, the Bohr model failed pretty miserably at. And the reason is pretty clear if we think about what it means to be a particle wave. So in our simple model, in Bohr's simple model, I should say, the wave only went around the circumference. However, matter waves are 3-dimensional. So real atoms have to have 3-dimensional wave-like properties. So how do we describe the atom in 3 dimensions? Well, it turns out that there is a gentleman by the name of Schrodinger who came along, and he was able to write down a 3-dimensional version of the quantum mechanical wave equation. So this is done by Schrodinger. And Schrodinger was interested in this thing that was waving, and again, we called the thing that was waving a probability amplitude. So if you want to know the probability of finding a particle at x position x, that was given by, well, let's say position x, y, z, since again we're in 3 dimensions. That was proportional to this thing which we call the wave function, which was a function of x, y, and z. It was a probability, the probability was proportional to that wave function squared. Again, this is called the wave function. Okay, so we can figure out the probability of finding a particle at any given location in space by looking at this wave function squared. How do we find the wave function? If we find it, we can square it and get the probability, but how do we find it in the first place? Well, to find it, we need to use something called the Schrodinger equation. Now, I have to warn you, this is a differential equation that we are not going to have to solve in this class, but it's important that you see it so that you know where it comes from. If you would like to solve the Schrodinger equation, feel free to take modern physics after this or quantum mechanics or some higher level physics course. But the Schrodinger equation is given by this, h bar squared over 2m. And there's this upside down triangle symbol thingy. Upside down triangle is called a Laplacian. And basically it's a second derivative if you have had calculus before. It's also a second derivative if you have not had calculus before, but hopefully that means something to you if you've taken calculus. Minus h bar squared, Laplacian over acting on the wave function. And then for the hydrogen atom, we're going to have a K, charge 1, charge 2. So this is the potential energy. And in general, this will be the potential energy, even if you're dealing with a quantum mechanical system that's not an atom. The potential energy times the wave function. And that will give you the energy times the wave function. So this is a differential equation. We can use this differential equation to figure out the shape of atomic wave functions. So if you go inside your chemistry book, or physics book for that matter, you will see pictures of different wave function shapes. Sometimes you get s orbitals, sometimes you get p orbitals, d orbitals, and f orbitals. Those orbitals, the shape of those orbitals is basically a plot of the function phi. So you might get an orbital that looks spherical, you might get an orbital that has kind of a dumbbell shape, you might get all sorts of different weird, funny shaped orbitals. All of these orbitals are just solutions to that Schrodinger equation under different circumstances. So the Schrodinger equation allows us to solve for the wave function in 3 dimensions. And that wave function tells us the probability of finding a particle at any point in space. And we have to pay attention to the fact that there are still these quantization requirements. What do I mean by quantization requirements? Well, whenever we've solved wave equations before, we've always gotten discrete values of certain quantities. So for example, the wavelength could only take certain values here. And when we considered the particle in a box, what we showed is that since the wavelength could take only certain values, and momentum depends on the wavelength, momentum could take only certain values. And since energy depends on momentum, the energy could only take certain values. So we had all these different quantized quantities that can only take certain discrete values. They can't just have any old value you want. We did a similar thing for the energy of the hydrogen atom. The energy was minus 13.6 electron volts divided by n squared, where n couldn't be any old number you want, it had to be a positive integer. So what caused these quantization conditions? Well, it turns out that the quantization, why we got discrete values, came about because of the boundary conditions. Here we had a boundary that said the box had a length L, and the wave had to fit within that box, so the wavelength had to be some multiple of L. Similar here, we had a circumference that was equal to 2 pi r, and the wave had to match up all the boundaries. So what we can say is that quantization has to come because you have to match up the wave on the boundaries. Now that gets a little bit difficult to do in 3 dimensions, because now you're going to have 3 different boundaries that you have to match up on. So when we were only working in 1 dimension, one-dimensional box, we only got 1 quantum number. Now that we're working in 3 dimensions, we have 3 sets of boundaries we're going to need to match up on. So we're going to have at least 3 quantum numbers. Quantization comes from the boundary conditions. In 3 dimensions, you're going to need 3 quantum numbers. So what are those quantum numbers? Well, one we've already talked about. One is n. Really say you need at least 3, because as it turns out, there's going to be one more that we're going to need. N is the first one. It's the same one that showed up in the Bohr quantization. This is called the principal quantum number. And it tells you the energy. For the hydrogen atom, it's this. For non-hydrogen atoms, this formula gets more complicated because the electrons repel each other. That changes the energy in a complicated way. But n can take certain values here. N equals 1, 2, 3, positive energies. What are my other quantum numbers? Well, there's another quantum number that we call L. This is the orbital angular momentum quantum number. It takes, this chooses what the total angular momentum can be. The total angular momentum is given by that quantum number L times the same quantum number again plus 1, whole thing times h bar. And L can also take certain values. This time it can be 0, unlike n, which cannot be 0. 1, 2, all the way up to n minus 1. So if n is 1, L can only be 0. If n is 5, n can be 0, 1, 2, 3, or 4, but it can't be 5 because it can only go up to n minus 1. Other quantum numbers. We have a quantum number, little m. This is called the azimuthal quantum number. Azimuthal. And this tells us how big the angular momentum is in the z direction. LZ equals, actually, sometimes you write this with the subscript L. M sub L equals M sub L times h bar. And put some boundaries on this. Let's see. M sub L can be any integer between negative L and positive L. So if L is 3, M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, or 3. If L is 1, M sub L can be negative 1, 0, and 1. So these are the 3 quantum numbers that arise because of the quantization, the need to quantize the need, try that again. These 3 quantum numbers arise because you have 3 spatial dimensions, each of which leads to a different quantization. The last quantum number has to deal with the electron itself. It gets the name m sub s, and that's actually due to the spin of an electron. So if you imagine spinning a basketball, the spin, you can imagine it's rotating clockwise or counterclockwise. And much like clockwise and counterclockwise, there's only 2 values there, clockwise and counterclockwise. So there's only 2 values of spin. S sub z equals s times h, where s can only be plus or minus 1/2. Now, these quantum numbers, they follow kind of a weird pattern, but that pattern actually helps us to make predictions about atoms. To make predictions about atoms, we need one more principle that comes out of these quantum numbers, and that's called the Pauli exclusion principle. So what Pauli was able to deduce is that if one particle has these quantum numbers, the math actually doesn't work out to put another particle in there with the same quantum numbers. It's not just a matter of the particles are repelling each other so that two electrons are repulsive. It has nothing to do with that. It has to do with the fact that the wave functions will actually interfere with each other so that the math literally doesn't work out. So it's not so much that there's a force, so much as the rules of mathematics do not allow it. So how does the Pauli exclusion principle work? It's very simple. All it says is that no two electrons, or any, well, yeah, we'll say electrons, no two electrons can have the same quantum numbers. Actually, I'll say have the same set of quantum numbers. So let's see what quantum numbers we can have. Let's just list out the possible values. N, L, M sub L, M sub S. We're just going to fill these up from lowest number to highest number. We're going to start with N, since that determines what L can be, and L determines what M sub L can be. Lowest number N can be 1. Can't be any lower than that. N can't be 0. If N is 1, we know from the rules that L has to be 0, because L can be anything from 0 to N minus 1, and the only number that fits is 0. M sub L can be anything from minus L to positive L, but the only number that works for is 0. M sub S can be plus or minus a half. So there's two sets of quantum numbers here. 1, 0, 0, 1, 0, 0, 1 half, and 1, 0, 0, minus 1 half. That means that there are two, this gets us through 2 electrons. So that gets us every element up to helium. Hydrogen and helium. Now if you note, if you look at the first row of the periodic table, there's only 2 elements in it. This is just our first row of the periodic table. Let's go to n equals 2. If n is 2, we can have 0, 0, plus or minus a half. But if n is 2, we could also have 1 minus 1 plus or minus a half. We could have L is 1, M sub L is 0, or M sub L is 1. Because, again, if L is 1, M sub L could be minus 1, 0, or 1 because it can go from minus L to L. All of these guys can be plus or minus a half, so I'm just going to fill that in. But notice what we've done here. We've got 2, 4, 6, 8 possible quantum numbers. These 2, that gives us 2 atoms. That gives us lithium and beryllium, which are the next 2 atoms in the periodic table. And then we have 6 atoms from here. So 6 atoms. This is boron, carbon, nitrogen, oxygen, fluorine, and then neon. All of these are the second row of the periodic table. So what we're doing here is we're using these quantum numbers. We're using everything that we have built up in physics. From the Newton's laws, we applied that to electric charges inside the atom, protons and electrons attracting each other. We applied our quantization condition. We've applied what we've learned about waves. We're using all of this thrown into Schrodinger's wave equation, which gives us these allowable quantum numbers. And these quantum numbers, just using the math of these quantum numbers, we can derive the periodic table. That funny shape that it has, that when you first take periodic, when you're first freshman in high school and you see the sophomores taking chemistry in high school, and you're like, that periodic table looks big and scary. Why does it have that weird shape? The weird shape just comes from these numbers. Just comes straight from physics. You can predict all of the properties of atoms just by looking. You can predict all of chemistry. You can predict all of chemistry. You can predict all of biology, etc. You can do that just by looking at the physics of what's going on at a microscopic level using quantum mechanics and everything that we've learned so far in this semester.